All right, boys and girls, out of the goodness of my heart, let me give you some tips on some of these problems. So on number 2, the whole key to that is that you have two identical spheres and start with F equals big G M1 M2 over D squared. These two masses are identical. Let one be x, let the other one be x. Not to insult your intelligence, but I'm sure you can figure out what happens when you multiply x times x, solve for that, make the units work out. On number 3, here's the Earth. You want to figure out how far you've got to be so that when you drop something, you get an acceleration of 3 meters per second squared. So, you know the mass of this rock that we're on, and you know your acceleration. Find your radius. Problem number 4, similar type idea. Think about this. You got little g equals big G mass over r squared. The top number is not going to change because you're told, wow, the mass of the Earth really doesn't change. And so what's going to happen is that you can take that same mass and you're going to shrink it down by half. Wow, that looks like a jacked up pumpkin there. Okay. Anyway, so look what happens here. Keep in mind that value is squared. On number, which one do I want? Number 6. So here's the proton, here's this electron moving around, okay? So you want to find the gravitational attraction between that tiny little bit of matter we call an electron and that big massive thing we call a proton. If 6a is wrong, everything is going to be wrong. So your answer to 6a should be something times 10 to the negative 47th power. Mainly because you got a very, very tiny bit of matter, doesn't distort space-time very much. Proton, a little bit bigger, actually it's 1,000 times bigger. But find that gravitational attraction, and what you'll see is that that electrical force over that same distance is much, 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 much stronger. On number 8, pay attention to this. Here's the moon. Here is the Lunar Command Module orbiting said moon. Okay? Like that. And here's the whole key to this one, is that this is 72 kilometers above our nearest big satellite. And with that one, I've also given you the radius of the moon itself, 1738. Let me give you a hint. Add the two numbers together. That's going to get you your radius. At that point, it's a plug and chug type affair. So on number 8 and number 9, just like the Earth, you should get answers of 10 to the 3rd. That's kind of cool. All right. Moving on to number 10, we started those in class. On number 12, and here's Saturn, and we'll kind of draw in its rings just because we are cool. And you're going to start with that. Mass 4 pi squared. R cubed equals big G. No, I'm sorry. It's been a long day. 4 pi squared r cubed equals big G M and t squared. solve for mass, that's t squared. And anyway, make sure that you pay attention to that value of period. I was a jerk and I didn't give you in the correct units. You need to roll that thing into seconds. And that answer should be 10 to the 26th power. Change it up a little bit. Okay. On number 14 with the geosynchronous orbit, so here's, we can make it blue, here's our Earth, here's the satellite. We want this to orbit above the same point all the time. So basically you're going to let the period equal 24 hours. Oddly enough, don't leave that in hours. And you're going to go back and you're going to find that radius. Let me give you a hint. It's going to involve a cube root. And that radius here should be 10 to the 7th. And then, but it asks for the distance above, so you subtract out the radius of the Earth. And there you go. So on number 15, then that's actually number 13. So number 14 is a similar type deal. The only thing on number 14 is you're using 90 minutes instead of 24 hours. So on number 14, you're going to use the exact same equation that you did on that one. So old school on that. On number 16, you're going to go old school, v squared equals v naught squared plus 2ax. And oddly enough, when you jump up, remember that your final velocity is going to be 0. What you're searching for is that initial velocity. When you get to 18 through 20, you're going to look at escape velocity. Basically, here it is. How fast do you have to throw something so that it completely leaves that gravitational field? And then that's going to lead into this concept of black holes. So if all goes well on number 18, your answer to number 18 for that escape velocity should be times 10 to the 3rd. On number 19, that answer should be 10 to the 4th. And on 20 for the grand finale, the mass would be 10 to the 35th if the sun turned into a black hole, which would be bad for us for any number of reasons. Anyway, there are some helpful hints. Live long and prosper.